Okay, so today we're going to be talking about 3D models or 3D meshes. Basically a way to set up more complex objects than only like the basic box and sphere that we've been working with until now, which we can fairly easily represent geometrically and set into vertex lists. We're going to look at ways to basically store in files information about more complex objects than that. So to begin with, we're going to look at a pretty simple file structure just for a simple mesh, but it's a pretty general one. And we're going to look at a more specific file structure that has more complex meshes that can have different materials and different objects and different kind of nodes which have different transformations within the single object, which will act as a single object in the end. And finally, if we have time now, we'll look into the code a little bit, how we can read that file, how we can look at it in the program and kind of visualize this. So to begin with, what we're trying to set up is a representation of either a simulation of a real object or a representation of some imagined object that we want the user to be able to view on the screen. So these different objects, which can be something like houses or landscape objects or characters in computer games or in animations, we need a way to represent a single object like that, and we need to be able to move that object around and look at it from different points of view in different places, move it around, rotate it, and basically work with that single object as a single entity in our program. But at the same time, we need its whole kind of local geometry to be unchanged throughout all of our transformations. So we can imagine it being any of these things, describing the outline or the surface shape of a three-dimensional object. A model can be a mathematical representation of, or a graphical representation of some mathematical concept or mathematical form, or anything that we can put forth as a 3D form. So the base data of our object, and we've already looked at this a lot, obviously. That is the vertex list that we've been sending in for the basic cube and for the basic sphere. But now we want to make this a little bit more general. So the first part of our graphic representation is this list of vertices. And we can just imagine this as being points along the surface of an object. So if we imagine a human face, we simply kind of simulate the shape of that by sampling points on different locations around the face or around the geometrical shape, and this will serve as kind of our position surface or surface kind of positional data. So in the cube, these are simply the corners of the cube. So we have 8 vertices in a cube. The way we've been representing them until now, we've actually had to have more vertices than the 8. Even though the actual vertices of the cube are 8, we have to read through the list in a specific order, so we're kind of duplicating some of them to be read as part of one side, and then the same vertices as part of another side and the third side. So each vertex is part of 3 sides, so we have to triple that vertex. And we'll look at how in some cases we can not do that. That is how we can kind of refrain from doing that and representing each vertex only once in the list. But in some cases we actually need to do it anyway, just because of the way we send information into OpenGL. So the corners of the cube, the sphere, we've already looked at its representation. We simply kind of went through a double loop with 2 sinus and cosine functions going through the angle around the globe vertically, or around the longitude of the globe, and then along the globe horizontally, or along the horizontal kind of latitude lines. And we just evenly distribute points along the surface of the sphere and say this is our point list. And approximation of more complex objects, there's a P missing there, a more complex object like the human body for computer game characters and so forth. But the question is, after we take this kind of sampling of points along the surface of an object, how can we take this and make it into a collection or make it into an even surface or an actual enclosed object or a solid object. So, as we've already looked at as well, and seeing as this lecture is coming at this point, both the kind of polygonal meshes that we're looking at now and textures later on, we already have all of the key ingredients for this. We've already worked with polygons, we've worked with vertices and normals, and we've worked with all of this data. So building polygonal meshes isn't really a complicated thing to understand at this point. It's just taking what we already know and kind of structuring it in a specific way. And we already have polygons, and they basically fill in the space between the points. So simply enough, if we have the cube, we take 4 corners together, and we say these are going to be a single quad or 2 triangles that will simply fill in the surface of one side of the cube. We do that 6 times, we have 6 sides of the cube, and the entire thing is enclosed at that point. So we can say once we've drawn these 6 sides, we've enclosed the space in between. So while we're actually representing a hollow object just made of kind of infinitely thin polygons that don't have any weight and don't have any thickness, once we've enclosed the object, we've made a representation of an actual kind of 3-dimensional solid object. And that's what we want to do with more complex objects as well. Approximate points along its surface with the vertices, and then enclose it with polygons. And the polygons enclosing the thing, then it's up to either animations or motion or sound to make them actually feel heavy and solid. But by enclosing them, at least we've taken away this feeling that everything is kind of paper thin and just kind of mathematical objects that don't have any thickness and don't have any weight, but represent something that's real. And like we've talked about with the cube, each vertex in a cube is actually part of 3 sides of it, part of 3 polygons. Or actually, it's part of 4 polygons in the case when we represent each side with 2 triangles. But either way, each point, each vertex in a model can be a corner in many different polygons. So we don't want to have to represent the polygons and re-represent each vertex every single time. We need to do it in some cases, like the cube, where we just read through the normal and vertex list side by side. But in some cases, as we'll look at, we can represent the vertex and the normal only once in a list, and then just index into it and talk to it multiple times in order to draw different polygons that still use that same vertex. Okay, so we need to keep some collection of points and a collection of polygons, and we can set this up simply as lists. And yeah, we'll look at these indexing later, but first we're going to look at one more piece of data that we need, which is while we already have the position of each vertex, so this kind of surface approximation with points, and then a way to combine them with polygons in order to enclose the space between them, in order for them to look right when we start lighting them, we need the normals as well. So each vertex, when it's part of a specific polygon, needs to have a direction associated with it as well. So the data that we need in order to draw a polygon is which vertices are part of this polygon, and for each of those vertices, which direction is that vertex facing. And this is not so that the enclosed space will be correct geometrically, but in order for us to be able to calculate the lighting and calculate the color correctly, so that we'll actually get this real 3-dimensional feel that doesn't come only from the geometry and the positions, but mainly really from the lighting and from the colors, or the lighting and the shading. So in this picture here, we're imagining each polygon to have a normal. So this house here would have 4, 5, 6 sides, 7 if we count the bottom as well, and each of those sides has its normal. And the normal is simply a vector which tells us which direction the polygon is facing, and we can calculate that fairly easily. But in most cases, when we're going to be reading files, the normals will already have been calculated and written into the file. So we simply read a vertex list and we read a normal list, and then we structure them inside our program in a way that we can send them quickly and easily into OpenGL and have OpenGL read the correct vertices and normals for each polygon in a way that's as quick and as optimized as we can. But for this image here, we're imagining that we have a normal vector for each side, and that's simply the side that the direction that the side is facing. Okay, so more on normals. Here we're making the house a little bit more complex by saying, while we can calculate the normal for each side, when we actually draw it into OpenGL, we have to tell OpenGL what normal is associated with what vertex for every single vertex, even though it's the same normal for all the vertices in a single polygon, as in the case of the cube or this house, which is supposed to be flat shaded. So all of the vertices in a single polygon are directed the same direction, but because of how OpenGL works, how we send data from these lists through our shader, we have to make sure that when we call the main function of the shader for each vertex, that it has a specific normal associated with it as well. So in some older implementations of OpenGL, you could simply set a normal, and you could set up your shader in that way as well. So if you set up your shader not to send normals in as a list with the vertices, but only read vertex lists, you could set the normal in simply as a uniform variable in your shader. So you can say, I am now just going to set a normal, and until I set the normal to something else, this is the normal I'll be using. So it's possible to do that and say, I'm going to set this normal, and now I'm going to draw this side of the house in 2 triangles. Then I'm going to set this normal, and I'm going to draw another side or part of the roof, and so on and so forth. But the way we're going to be doing this is we're just going to read all of this data, both vertices and the normals, into lists. So we're going to have 2 adjacent lists, or basically 2 kind of parallel lists, one with vertices and one with normals. And for each index into those lists, we'll use the vertex and the normal at the same position, at the same index in both lists together, and send them that way through our shader. So our idea is to have, as we can see here, you can see that vertex 1, vertex 4, vertex 3, and vertex 2 make this side of this house. And when we're drawing using these vertices to draw this side of the house, we have normal n1 associated with all of them. But when we're using v1 and v4 to draw this side of the house, along with whatever vertices we have here, here, and here, we have v1 here, we have v4, and we have a different normal here. So in the case of the way we're going to read this data in 2 parallel lists, we actually have to make a new entry in that list for vertex v1 when it's part of this side here, because then it's using this normal, and we have to be able to index with 1 index into it. So v1 would also become v5, because it needs to be a different vertex when there's a different normal associated with it. Does this make sense? Okay, so in this case, we're going to have to duplicate normals. No, duplicate vertices, because when we're using the same vertex as a part of different sides, we're using different normals as well. And since we have to have them parallel in the lists, we have to make a new entry in both those lists. Even though it's for the same vertex, it's for a different normal. So we're really making entries of vertex normal pairs, and we can only reuse it if we're using the same vertex normal pair. And so we can go over to this image here. So a cylinder like this, we could imagine that we're just going to draw it like a hexagonal cylinder of some sort, and we'd have the same normal associated with all the vertices in this side. And so when we display it, it'd end up being kind of obvious which side is which. It would be flat shaded. But what we want to do is we want to kind of fake smoothness there. We can see in the image here that it's hexagonal. It's just 6 sides on this cylinder, but we're using those 6 sides to approximate a circular shape. And the way we do that in using the normals for the lighting is that we say I have a normal n here, and this normal is going to be part of V1 when it's part of this side here, when it's part of this face F1, and it's also going to use the same normal for this vertex V1 when it's part of this F2 side here. I don't know why there's this V2 pointing here in this case, but what we would do here is to say V1 and N here are a vertex normal pair, and I'm going to use them for both face 1 here and for face 2, ending up with a smooth transition between them. Because at this line, we're basically going to end up with the same color in the lighting calculations. So we get the same color in this vertex for V1 as part of this face, and for V1 as part of this face. We'll have a different normal here, which will be used as part of this face and this face. And then the relationship basically between our vertex shader and our fragment shader will make sure that the transition here will be smooth from the color that's in this corner all the way up to the color that's in this corner, which incidentally is the same color for this face in this corner. So we'll get the same color basically on the edge, on the adjoining edges of these faces here, and then we'll gradient from that, or interpolate from that color over to the color here. Okay, so that's the idea of getting smooth shading. We'll look at that in the program later so you can see better how this is happening. So I'm talking about quads here a lot. In the program in the end we're going to be looking at triangles pretty much solely. But in this structure that we're going to be looking at here, here's actually an image of this. We're going to be using polygons with any number of vertices. This is a very general type representation that we're going to be looking at first. Then we're going to kind of constrict it to a specific triangle-based representation for OpenGL. So here we have the house, which is flat shaded. It has the same normal for each vertex when it's part of a certain face, and then another normal for the vertices when it's part of another face. Here, the same thing. This vertex when part of this face will have one normal, but the same vertex when part of this face will have another normal. Here, however, you can see the vertex is still here, and it's facing, it's part of the face that's facing this direction, but we take an average between the vertex, between the normal of this face and this face, and say this vertex is going to have that average normal when it's part of either face. And so we get the same color down the line here, part of both polygons, and then we get this interpolation of the color throughout. So this is an approximation of the smooth surface. So okay, now we have basically this data of the model or of the mesh. We have the normals, and we have vertices, and then we have polygons. And now we just need, well, it differs between file formats, whether you're just looking at making the file as small as you possibly can, or if you're looking at having it read the fastest, or have it structured so that your program structure will read it the easiest. But we're going to imagine that we just want the file to be as small as we possibly can for this representation that we're going to look at here. So we're going to try to not duplicate any vertices and not duplicate any normals, and then just have the polygon list index into both of those lists in order to set up this basic barn here as an example. So this is the full data for that barn image. We have seven polygons here, so we're representing the bottom of the barn as well. We have 10 vertices. So we can go back here. There are simply 1, 2, 3, 4, 5 on this end, and 1, 2, 3, 4, 5 on this end. And that's all the vertices we need. We have 7 normals. That's 1 straight down, 4 to the sides, kind of the horizontal sides, and then 1 for each part of the roof. So that's 7 normals, and then we can see how we're representing each face. So the first face would have to say that it has four, basically it's a polygon that has four vertices, so it's a quad, and it simply says the indices into the vertex list are 0, 5, 9, and 4, and the indices into the normals are 0, 0, 0, 0. So we can see this is flat shaded, so in all cases each face has the same set of normals. But if they were different, we'd simply read and say, okay, the first vertex will have the first normal here. The second vertex will have the second normal, third vertex, third normal, and so on and so forth. So we're doing double indexing here. It's indexing specifically into the vertex list and specifically into the normal list. In the end, when we're going to do this in OpenGL, we're going to do this differently. We're going to, as I said before, we're going to have these parallel lists and we're going to have one index. So when we set up our index list, each index is the index into both the vertex and the normal list. So we can't save space as much as this does, because if we were going to do the basic barn in that file format, because it's flat shaded and each vertex uses a different normal for the different faces that it's part of, our vertex list would have to be a whole lot longer, and then our normal list would be exactly as long as the vertex list, and we'd be duplicating a lot of that. What we'd gain by that, though, is that even though our file would be a little bit bigger, we could read this straight into OpenGL and have OpenGL process it that much faster. So in some cases it's not always best to have the least amount of space, but instead we have OpenGL optimized to read through these lists in parallel, and so we're going to use that, and we're going to set up our file structure in a way that kind of capitalizes on that. But so this is a simple file structure that's good enough to be able to represent pretty much any three-dimensional object. It's going to get a little bit hard to handle when you have a really, really big object, but if you just have a program that reads into this representation would be as good as any. Then you can just decide, am I going to have it actually in text format, or am I going to set up a binary file with this data? Yes?
Could you save more space if you calculate the normals?
Yes. You could save more space by calculating the normals, and I've worked with actually a lot of file formats that do that. So most, or a lot of file formats associated with kind of 3D modeling studios and stuff like that, or 3D modeling software, a lot of them will allow you to decide whether you actually save the normals in the file, so pre-calculate the normals, or if you calculate them in the program. What this means, though, is you need a specific way to calculate them. You need to specify how these normals should be calculated. So you can say something is just flat shaded, and that's simple enough. And you'll get these vertices, and you'll get these polygons here, and you simply say, if it's flat shaded, I'm just going to take the vertices in each polygon, and I'm going to take either some kind of cross product, or in these slides we have a different kind of type of taking the cross product over vertices in a polygon, and I can calculate that normal. And then I'll just use that normal for this face. But then I have to specify that it's flat shaded. If I want it to be smooth shaded, I'd have to have some specific way of calculating that.
For a moving object, don't you have to calculate the normal?
For an object that's
rotating or...
if it's a rigid object, but it's rotating, you don't have to recalculate the normal, because the normal is sent through your model view matrix or your model matrix just as your vertex is.
Okay.
So you have the model matrix that you use to rotate things, and that's part of your shader, and both your normals and your vertices are sent through that. So this data here is basically the data represented in local coordinates. Then you have your model matrix that you send your local coordinates through to take them into global coordinates. So yes, you kind of do recalculate all the normals and the vertices, but that's what you always do in the shader anyway. One way to calculate smooth shading would simply be to say, for each vertex I'm going to calculate the normal, or basically I'm going to calculate the normal to all the polygons, and then for each vertex I'm going to take an average of the normals for every polygon that vertex is part of. So you can go through your system and you can find an optimized way to run through your system and do that. If your normals are representing a specific type of object, like a sphere or something like that, you can also calculate that just based on the kind of on the normal to the curve of the surface. Or if you're using something like Bezier curves or B-spline curves or something to represent the surface, you can also calculate the normal. But in the end, if you have a very, very kind of arbitrary and randomized object that you've gone into your 3D modeling software and really just pulled apart entirely and don't use any specific curves, you're going to end up having to calculate all the normals and then taking the averages. So that's fine. Another thing that a lot of programs allow is to say, I'm going to have this smooth, except if the angle between two polygons becomes less than something, or more acute than a certain angle, then I'm going to actually split that up. So these will be fairly complicated calculations, but yes, this is often done. The representation that we're going to use, though, that we're going to read in, is going to expect the normals to be pre-calculated in Blender, which is what we're going to use, and stored in the file alongside. So yes, you can save more space by calculating the normals, but then you also have to have in your file format in which way or by which kind of criteria am I going to calculate these normals. All right. Okay, so this is the data. Any questions on this idea? It's not a super complicated idea, and we've already basically worked with these vertex lists, except we've just set them up in our program rather than reading them from files. So I have two slides here just on calculating the normal. GL-enable, GL-normalize isn't really supported anymore in the way we're doing this since we're using these, since we're using the shaders. But you can set up your shader so that you can tell it whether it should normalize vectors or whether it should expect vectors to already be normalized or not. And so you can save a little bit of calculations if you can always expect your normals to be normalized and then skip normalizing them yourself, or if you expect them to be of any length and any size, and so you have to normalize them during the lighting calculations. But what GL-enable, GL-normalize did in the fixed pipeline OpenGL was basically it said whether or not during the lighting calculations OpenGL should divide with the length of the normal, or if it should skip that division and save a little time, save a little computation. So yeah, you can take 3 points from a normal and you can take the cross product between the vectors between them. So that's one way. If polygons are really small, or just if your space is kind of so that you're using very, very small numbers, just kind of floating point errors and floating point detail can make the normals not always as perfect. And as well, if you don't have a triangle, if you have a quad, then it's not necessarily true that it always lies in a plane, but maybe you still want to calculate one normal to a quad and then split it into triangles and use that one normal on it. There are different reasons, but here's a way to calculate basically the average normal to a polygon with any number of vertices. We're probably not going to end up using this, at least most of you, in our project, but it's nice to have it there just to know how you can pre-calculate this yourself. If you choose either to do normals differently or to read in different types of file structures than the exact one that I'm going to be demoing for you, you might be interested in having this because this calculates a really nice normal. You're going to have to normalize it though. It doesn't always give you a unit length normal. But then again, the cross product doesn't do that either. So, all right. So if there are no questions on just this file structure as it is, I think we can just go and look at a little bit of a more complicated file structure in our program. Is there anything you'd like to look at or talk about in this point? Okay, so in here I have a file structure that libgdx supports, and Well, libgdx supports both a binary version and this JSON text version of this file. So we're going to use the JSON one just to kind of, so that it's simpler to read actually what data is happening here. But if we look at the base data, okay, this is nice because we have a little cube part of this model here. So okay, here we have the data, the vertex data, oops, of this part of the mesh. So what's happening in this structure here, while we were looking at a fairly general structure, it was only describing one mesh. It was only describing this one house, and everything was in one vertex list and one normal list, and then we had indices into that. A proper kind of 3D model file structure needs to be a little bit more versatile than that. So what it has is, it has kind of various mesh parts that you can save, and then it has what's called a node, and each node will have a specific position and scale and rotation depending on the center of this object, the center point of this object, and then it'll have specific mesh parts that will be drawn using that rotation. And so if we start at the vertices, if we just imagine that we go into this simple form that we've been looking at, each node part is a mesh structure exactly like what we were just looking at in the file. So we have a vertex list here, and in this file format, the vertex list is actually interleaved. The vertex list and the normal lists, they're interleaved. So here we have the first vertex, and here we have the first normal, and here we have the second vertex, and here we have the second normal. And because this is made by a program, there's really we can't depend on there being any structure on in which order this is. If I would have gone in here and just picked this in with my hands myself, there would have been some structure on this, but this is just the cube, and we can count the lines. 4, 4, 1, 2, 3, 4, 4, 1, 2, 3, 4. Okay, so we have 4 vertices for each face, and we have to kind of redefine each vertex for each face, because this is a flat shaded cube. Just like, sorry?
Did you say a program made this?
Yeah, program made this file.
So is that why we have -0 there?
Is there a -0 here? Oh yeah. Yes. Okay, I hadn't looked at that.
It's probably the same as... Yeah.
It's definitely the same as 0. Maybe this file was made from floating points with more detail, like a double, and there was some small variation from 0, and then it makes the files and it stores everything in floating points, and we just don't have the precision. The floating point precision isn't as much when it writes it in the file. Something like that might decide that. I'm not exactly sure. But again, yes, it's written by a program. The program just writes something. And in most cases, when you have your file reader and your file displayer properly set up, and then you have your 3D modeling software like we have Blender, once everything is set up nicely, you're never going to open that file and read it yourself. So you don't care if it's -0 or +0. But we can, if we look for this vertex here, again, can we find -1? Yeah, here it is again. Here it is part of the face that's turned to -1 in the z direction. So this is the face that's turned away from us, whereas this is the face that's turning straight up. But this vertex here is part of both of those faces. And we'll probably find it in a third place somewhere here. Yeah, here. And here it's part of the one that is turned straight down, -1 on the y. So this vertex is part of all of these faces, but because this is a flat shaded object, this cube, then even though the vertex is there 3 times, the vertex normal pairs are 3 separate vertex normal pairs for that vertex. So it's set up 3 times in this file here. So here are the vertices and the normals. So in this case, the vertex list is a single list. it actually has attributes here, and it says position and normal. This file structure would allow me to add here and say, I don't remember if it was UV or UV chord, something like that, and say, okay, this means that there will also be 2 more numbers for each vertex. So now I have 6 numbers for each vertex. By saying UV chord, I'm going to say I have the texture coordinates for each vertex there as well. And there are 2 coordinates, so then I'd have to read 8 numbers instead of 6 numbers for each vertex and set them into different lists: the vertex list, the normal list, and the UV list. Let's not dwell on that for now. So reading this, and I've set up a fairly simplified reader of this. It can read any file, but it'll ignore a lot of stuff. So my reader, as it is now, only reads position and normal data. If there's more stated here, which means then there will be more numbers in the vertex list, I simply make a vertex fill number and I ignore the rest of the numbers for each vertex. So I read 3 into the position, 3 into the normal, and the rest of them I ignore until I get to the next vertex. But in this case, yes, we have vertex normal pair, vertex normal pair, vertex normal pair, and here in parts, the part is basically a polygonal mesh. So here I have the vertices, which don't need to be only for one mesh. These vertices could be, in fact, we have another part here which is much more complex, as you can see. We could, in this file structure, combine the vertex lists from both of them. We can just say, we can make one big vertex list, and then each part, which is each mesh, will be indexing into different parts of this. And that just depends on the program or the translator that translates into this file format. But if we look at this, we're basically saying this part here has some ID. It has a type, which says we're going to read triangles, which means we're just going to take 3 numbers and read them together, the next 3 and read them together. And it says I'm going to take vertex 4, 5, and 0 and read them into a triangle. So we have 0 here, 2, 3, we have 4 here, and we have 5 here. So this, and this vertex, along with this, and this normal, will be read into a single triangle. And we can see that these just so happen all to be vertices with the normal -1, 0, 0, which is normal because this is a flat shaded object. So each polygon will probably always have the same normal on all of the vertices. So here's a triangle. The next triangle is 8, 6, 1. So that's this one, and this one. And they'll probably all have 0, 1, 0, 0, 1, 0, and 0, 1, 0. Some of the zeros with -0, but doesn't matter. And so on and so forth. Okay, so just looking at this, are there any questions right now? Okay, we can look into OpenGL here. Do you want to take a break or do you want to just finish?
Yes.
All right. So I'm going to go into Boxgraphic here. It's more or less the same file, except I've actually added these UV texture coordinates. We'll look at them if we have time today, or otherwise we'll look at them after the weekend. But if we look at what we're drawing here, if we just look at the pyramids, we've already had them in the program all the time. They look exactly the same. But I'm drawing these boxes, these cubes, a little bit differently from what we did earlier. So I still have my vertex array, and I still have my normal array. But what we did earlier, is it here, still here? No, it's not in the draw solid cube function anymore. But what we did earlier was we called draw elements several times, once for each side, and basically reading different parts of this. So we're reading basically these 4 together as a triangle fan. basically going the circle around. And then we're taking the next 4 together as a triangle fan, and so on and so forth. We couldn't have just done triangles, because then we take these 3, and then we take these 3, but we want to take these 3, and then we want to take this one, and this one. So okay, we could do triangle fan, but then we had to do 4 and 4 at a time. So we had to call draw 6 times rather than only calling draw once. So we haven't changed the vertex array, and we haven't changed the normal array. So we still have the first, the normal at index 0 is the normal for the vertex at index 0. That's the same way as we did this before. The difference now is that we've added one array here, this one, which is here, which is a short buffer. So it has integers, small integers, and these integers are simply indices into the normal and the vertex arrays. So now I'm saying I'm going to draw as a triangle 0, 1, 2, and then 0, 2, 3, which is the same as calling triangle fan did earlier for the first 4. Then in the next line here I have 4, 5, 6, 4, 6, 7, which is again the same as triangle fan did earlier, except for the next 4 vertices and normals in the lists. But I'm putting this all into one index array, and I'm just saying I'm setting up, and I just hand wrote these indices into this to make this cube. And so now I have a vertex buffer, I have a normal buffer. Let's ignore the UV buffer for now, but we can add that as well. If you want to look at the UV buffer, it's again the same amount of vertices, except each vertex here is only 2 numbers rather than 3. But again, for the index at, say, 2, we have this vertex, and it's associated with this normal, and it's associated with this UV coordinate. And the indices, the index list here will index into all of them. So now we're saying, when we call draw elements, we're telling OpenGL, you're going to draw triangles, and you're going to draw you're going to get a buffer with 36 values, which is what you're going to draw. The buffer will have short. We could also do it with byte or int, I think, or at least OpenGL allows int, but I think libgdx has some restriction that it's best to use short. And then we have the index buffer, and the index buffer just holds these shorts. And what OpenGL will then do is say, okay, you've set all these attribute pointers here to these different buffers, and you've told me how to read them. These ones 3 and 3 numbers, this one 2 and 2 numbers together. Now I get 36 numbers in a short index, and so what OpenGL will do, it'll just take the first one and it'll send it through our vertex shader, and it'll say, I have all these attribute pointers, so I'll just take the vertex at the first index, the normal at the first index, and the UV coordinate at the first index, and I'll send all of them into your shader. Then it'll take the next index, do the same, call the main on the vertex shader, it'll do the third one. Once it's sent 3 vertices with its normals and its UV coordinates through the vertex shader, it'll take the 3 of them together and say this is now a triangle, and I'll send it through the rest of the OpenGL pipeline together, meaning that those vertices will be used together to interpolate the color between the vertices, sending the right data into our fragment shader. Okay, at this point, questions or good ideas? So what we're looking at now is simply box graphic, drawing that same simple cube, except it's drawing it in a different way. Rather than telling OpenGL here we just have these 2 buffers, and we're just going to read linearly through them. So if I ask you to read 4 numbers from them, or 4 indices from them, you'll just do 0, 1, 2, 3, and then 4, 5, 6, 7, and so on. We can now read through them in any order. And obviously here it's very structured because I had to kind of get my mind around setting this up. But if we go back into here, this is not as structured because a program did this and it just took the triangles in whatever random order. But that's fine. These are the indices that we will then read into this buffer of short integers, that we send into OpenGL. This is what we're going to set into the vertex buffer. This is what we're going to send into the normal buffer. And so we'll have all these buffers, and we can do all of this and simply draw this. What this file structure has as well, not only the indices and the vertices, it also has more information. For instance, here it has materials. So in this particular model, we have 2 different materials. I don't think I'm even reading this ambient, but there's a diffuse value here that I set specifically, and there's a specular value here that I set, shininess. So all of these are just numbers that we can easily set into our shader before we draw. And so we have, in our root, we have materials, and they have specific IDs that we can use to index into them. Or I basically use these string IDs while I'm reading the file. I don't actually index on string IDs while we're drawing, but we kind of set up our structure using these string IDs. So we have 2 materials here. Then we have the meshes, and each mesh has some amount of parts, and the parts are basically tell us how we want to draw from the vertex list and give us a list of indices into the vertex list. So we can have more than one part as part of this mesh. And the parts, no, they're linked in a different place with material. So then we have the vertices. So here we're indexing into the vertex list of this part. Here we begin another mesh. So meshes in this case has 2 meshes. The first one is this cube, which is super simple. The next one, okay, here we're just going through the index list. Okay, so in a text file this is a lot. So obviously we will usually be using binary files to read and write this, because we don't really, it doesn't help anyone to try to human read a file like this, whether it's text-based or not. So having a JSON file here, you know, big deal. Indices, indices, indices. All right. So indices stopped, and this is supposed to be drawn as triangles. Now we have vertices. Again, a lot of vertices. Yeah. All right. Okay. So now we have materials, and we have meshes, and each mesh has a vertex list and a list of indices, or actually maybe several lists of indices for each part, and the parts have IDs and stuff like this. So we have all our data there. Now we need to actually set this data together and say what we're going to draw here are nodes, and each node has an ID for its material. So this is the material we're supposed to use for this node. That is, it describes the color and the surface and the shininess of this object. And here is the mesh part that you're supposed to use. So that's some ID that's made by the program as well. So we end up with a material and a mesh part, which is basically an index list. And this part here, in this case, also has a translation. So it's not positioned in the center of this local coordinate frame that this model is drawn into. It's offset by this number. And then we have something that has the ID, how would this be pronounced? Ecosphere? Ecosphere? I don't know. I don't remember. I've never had to talk about this form. It was this sometime before I went into Blender and kind of stretched it on all around. So it's basically just a random blob. But yeah, it has an ID for a material, it has an ID for its mesh, and it has some position. So it only has a translation now. Once we've looked at this, we can actually go into this file and maybe change it around and see what happens in this. Add a rotation, change the material. But I'll just show you what this looks like. Okay, so this is the object that we're looking at. And yes, it's a single object. This cube here and this blob here are part of the single object. That's just because I just went into Blender and I just put some stuff there and made a blob and then.
And Blender generated the file we were looking at.
Blender generated, well, actually through a kind of add-on, an export add-on. So there's an export add-on, and in order to build these files, you're in the end going to have to get a specific version of Blender, not the latest version, because some of the things have changed. You can use the latest version and you can still export, but it doesn't export the materials right. So this export add-on doesn't understand the way the material is represented now, so you just get a default material and everything. You can still use it and export it, but you're going to have to go into the text file and edit the material yourself. It's not a big deal. You're not going to have to go and edit the actual vertices or anything. So that's not a huge deal. But if you get version 2.69, I think that's the latest version where this exporter works nicely. And then you have to get this exporter and add it into Blender, and then you can simply export as this file format. So it's all rather simplistic. Obviously, the actual Blender files and more professional files have a lot more versatility, but this is a nice way to kind of grasp what's happening here. So if we actually go into game here, to begin with, I'm just going to show you where we draw this. So here I'm just calling model.draw, and that model is this mesh model here. And I say model equals this load from file, and I set this file in here. We can look at the reader better later on. Then we get the model itself, and we draw it here. So if we were to add something like a rotation here, so I've added some rotation functions into model matrix as well. Look at that as well if we have the time. Okay, so now I just added that one rotation and drew that model. So yeah, the model is just this whole thing is one model. It doesn't make very much sense that these things are part of the same model. But either way, now they're just rotating around this arbitrary vector there. So these are two nodes in the same mesh. Obviously, when you actually want to make something proper in Blender, it's gonna have a geometry that makes more sense. But either way, you can see that the center is somewhere inside this object here, whereas this one is offset more. So if we look at the file again here, you can see that this node here is offset by very small numbers. So the center is somewhere close to the center of this part. However, this one is offset, especially in one of the directions, a fair amount outside. So we have a center to this object, and the nodes, we should actually just go ahead, Blender, just look at this here. Let's just open this file. Okay, I'm not good at Blender, I'll tell you that, but if we just go into this ecosphere here, there are a few things in here that we can use to edit this. So this is, here is the geometry, right? So the transform, and here we just have location and rotation and scale. So you can do this with tools inside this format here, but it's nice to simply, so I can rotate this in all directions. I can scale it separately in each of these, on each of these axes. Okay, then we can take the cube and say, right, let's do something similar for the cube. Let's scale it up in one direction, down in the other. Well, then I went to minus, down in the other directions. Let's make it impale this blobby object here a little bit. Wait. Like so. Again, I'm in minus here. Okay, fair enough. So now we have something completely different. Wow, it's hard to control this. Let's go to the ecosphere again and scale it up a bit more here. Alright, whatever this is now. So file, I'll just save it. So we need to go into export. I've added this libgdx G3D text format here, and we'll just export this and see what happens. Let's go in here and here. So okay, we exported this file here. Just gonna stick it back in assets, models. Yes, overwrite. Okay, so there should be a change here. For the first part, we have both a scale and a translation on the cube now. And on the sphere, the blob, we have a rotation. We have a scale and translation. The rotation is a quaternion rotation. You don't need to understand that. But what I did do is, let's go into graphics here, model matrix. I did add 2 more rotation functions here. And after we return the assignment we're doing now, and before we start really working on these things, I'm going to just take a lot of this code and put it online. So you can start with kind of what I've already done with that. I'll just leave certain things out for you to fill in yourselves. So you don't have to write all this from scratch. Okay, so I've added a rotation that rotates by an angle around a specific rotation vector. And that looks like this. And I've added a quaternion rotation, where we take the quaternion x, y, z, and w. And the idea is that you can take any rotation matrix that only has a rotation and no scale or translation, just the 3x3 rotation part of a rotation matrix, and you can represent the entire thing in 4 numbers. So you can kind of save space on that. And it's a generalized way to take any rotation matrix and save it as 4 numbers. And in order to take those 4 numbers and make them back into a rotation matrix, this is what you have to do. And it's nothing I'm going to explain particularly. Just Google quaternion transformation and you can probably find this thing. And I'm going to give you this code anyway, so no one has to do this by themselves. But the idea now is that this rotation here is this quaternion rotation. So we read these numbers and we simply, when we draw, we send this into the rotation, we send these numbers into the scale and this into the translation. And so if we go into our mesh model here, okay, so mesh model just has some data, and the model loader here, which we're looking at, reads the JSON and basically stores all that data in there. The mesh model itself just has the draw function. And what the draw function does is that it goes through every node in the mesh. And if we look at the nodes here, each node has a part, or actually has a list of parts, but each node has a transformation. So we have the rotation, the scale, and the translation. So what we do in here is that we say for each node in this file structure, or in this model structure, we push the matrix in the beginning and pop it in the end, and we say we're going to add the translation from the file, we're going to add the quaternion rotation from the file, and we're going to add the scale. We have to do it in this order, otherwise it won't look the way it looks in Blender. Then we set this model matrix into the shader. Then for each part in the node, we basically read what material it was indexing to, or it was referring to, and we say we're going to set our shader diffuse, set our shader specular, shininess, and then the ambient and whatever you actually have in your shader. In my case, I don't even have ambient in my shader. I just use the diffuse value for that. All right. Then we say the part also links to a mesh, and when we read in the mesh, we read in the vertices and the normals. So we tell OpenGL the shader has a vertex pointer, and we want that now to point to this data here, and the normal pointer pointing to this data, and we want to read 3 and 3 numbers together. I'm setting these textures to null because we're not looking at them yet. and these UVs here don't matter again. We don't even have UVs for this now. I'm not reading them in, so I'm just using the normal list just to have some numbers. In some cases it's necessary to send something in because my shader is using basically those UVs, even though I have an if statement that makes it not do anything with them. The shader in some cases may crash if you're defining a variable and then not having anything in it. So that's the reason I'm sending this in. There are probably better workarounds for that, but for now this is okay. So then finally we do this, draw elements, draw triangles. Why am I doing 36 here? That's definitely not. Okay, that number is being ignored. I must have copy pasted this. Well, let's leave it there, and what's supposed to be here would be, okay, let's see, yeah, count. So I should have some vertex count in the node part as well. Anyway, it's obviously ignoring this and it just goes through the entire list of indices. So this is wrong, but we're going to leave it. So it simply says read through this index of short integers, and these indices will index into the vertex and normal lists. And so what we should get now is our new object here. It's scaled up, so I have to back a little bit out. Okay, so there it is now. Again, just some random objects there. You can actually look a little bit at the difference between. So if we look at this file, it's just under 300 kilobytes. If I go into Blender now and I say I'm going to pick this object here and I'm going to set the shading to flat. So okay, now we have the same normal for all the vertices in each polygon. So that's fine, except that means we have much more vertex normal pairs now. So for each vertex in that insanely long list that we went through earlier, it now has probably 3. So each vertex, this vertex here is part of 1, 2, 3, 4, 5, 6 polygons. All right? It was part of 6 polygons earlier, but we only needed 1 vertex normal pair because it used the same normal for all of those. Now it's using a different one for each one, so we're going to have 6 times as many vertex normal pairs. Okay, so let's save this and export as, okay, to begin with, this is going to take a while. Not too long, I hope, though. I don't know why that happened, but, oh, not responding. Great. Let's see. So we're writing a ridiculous amount of data into that text format. Might have just been nicer to make a new object that didn't have as many polygons to look at the flat shading. Okay. I did this before I had actually finished, so yeah, okay. So it's saved now. Go in here and see that it's now 1.25 megabytes while it was 300 kilobytes earlier, so a lot bigger, but we can still read it in our program. No, I didn't move the file from its current location here. Copy into here. So the reading of this works, but if we actually open this file here, the lists are just even longer than before. Well, the index list is the same length. The index list, there are no more polygons, but it's just more numbers, more longer lists that it has to index into, so it can't reuse any of the indices. And this is what it looks like. Okay. So now I can do something like, let's make the shading smooth again. Let's take this and go into material here. Yeah, I had some texture on it that wasn't working. Go into textures here. I'm just gonna remove that. Yeah. Okay, so we have material here with this diffuse value, so we can change the value of that. It's not getting any prettier. Like so, we can take the specular here and just put it to pure white, or almost pure white. Okay, so we have to set the intensity here as well for it to actually use this color fully, otherwise it'll use a percentage of the color. Okay, Phong shading, and more stuff that we can set here. We can take the cube and do the same for that. In materials here, set it to a different color. And hardness is what shininess is called here. Make that ridiculously low. Go and export it again. To the same file that we have here. Like so. Let's see that we're reading that correctly into our program. It's looking pretty cool though. Nice and shiny. Okay, so we've looked at, okay, I don't think it's necessary to go very deeply into reading the file itself. I think that's something we don't need to spend time on. But are there any questions on kind of how we're reading this format and what we're doing with OpenGL specifically? I'm gonna basically take all of this code, all the code that reads it in and sets this up, and just give that to you online. I'm gonna clean it up a little bit, but I'll probably ask you as part of kind of next week's lab assignment to write the drawing code, that actually kind of loops through the nodes and draws it. And for two reasons, both so you can practice that, and also because you've made your own shaders at that point. And so you might have different ways of talking to your shader than I have talking to mine. So it's not necessarily going to work to just take my draw function and send it over to you. But the same basic method, walking through the nodes, doing the transformations, and within the nodes walking through the mesh parts and drawing the actual meshes, setting the material and drawing the mesh. So that's the mesh stuff. Model matrix, I'll also give you the code that I added here. This we don't need to read. And then the way we use it is simply we call the model loader here, send it into the model, and then I think the only other place I'm using this is where it's actually being drawn. You want to look in more detail at Blender or add textures or add something now, or you just want to? There's something in particular you'd like to see done? I think we kind of covered the meshes. I just want to make sure they work.
What happens if you scale the model to a negative value in Blender? Will it flip the numbers, or will it always calculate
the negative value will simply be set in there. And if we look at model matrix here, if we add a scale and we have a negative number, we simply end up with a negative number. So yeah, it'll simply flip. It just a negative scale simply turns something around. And all normals will also then go through that negative scale, meaning that they'll turn around as well. So all the normals will work correctly because of that. So negative scales are okay. You're just flipping the blob around. So yeah, that would be fine. It doesn't ruin anything. So you can pretty much within what we're reading now, which is the vertices and the normals and the materials, basically the diffuse and specular, anything you do using that in Blender will come across correctly. But I'm not sure we're going to be able to use this file format to read textures and stuff straight from Blender. So maybe not UV mapping. What I want to do next week though is when we talk about the textures to go through at least 2 types of texture mapping so that we could do that ourselves. We don't have time now, I think, to go through that, but we'll do it Thursday. Look at textures, and I actually want to, it's related to what we were asking about with skipping the normals and not having them in a file. The same thing you can do with the UV map on textures. You can save the UV coordinates in the file, or you can simply say this is supposed to be textured with a spherical map, and this is supposed to be textured with a cylindrical map or a cube map. And the spherical map and the cylindrical map are pretty nice ways of texturing complex objects, and I think we'll just go through actually how that works and how we can use that to apply texture. So we actually don't need a UV map to be sent in. For instance, the blob there, if we just have a texture that we want to kind of enclose it in, then we can add that texture afterwards. And just to look at that a little bit, I can go through. Well, I've already added both a diffuse texture and a specular texture to the cube class here. So again, just these weird random images. We'll look at this in more detail after the weekend, but 2 things you can see here. Number 1 is you can see obviously that there's an image texture there. And what the shader does is it uses the color from that image texture instead of the diffuse color. So it doesn't add them up or multiply them. You can do that in your shader if you want. I decided to just say if I'm using a texture, diffuse texture, I'm not going to use the diffuse color value. So here I'm using the image as the diffuse and ambient. For the specular, I'm using another image. So I'm not using the same image or just applying specular on top. And we can see the difference. If I go in here and say I'm going to use my texture for the diffuse texture and nothing for the specular texture, go here and we can see how the specularity is just added on top. So we have the diffuse color from the image, and then we have the specularity added on top. But instead, I'm going to use a texture image here for specularity as well. And then you can see there's an actual texture to the specularity itself as well. And this is a really small texture made in Paint, which is why you can see it really pixelated. It's a 128 by 128, whereas textures in computer games now are pretty much always 1024 by 1024 or larger. For complex environments, people are using 2048 by 2048 textures by now. 512, 512 at the minimum. So, but anyway, you can still see that we have both a diffuse texture and a specular texture here going on. And what I want to do after the weekend is to begin with show you how we do this and how it works, and also take an object like this object and be able to do either a cylindrical or a spherical texture map on that. So we can texturize that without actually getting a UV map out of Blender, but instead just adding the texture ourselves afterwards. In the end though, when you actually want to be able to make something in Blender or in Lightwave or in 3D Studio Max and just import that, these really simple importers and this kind of JSON format and stuff that we're using now is not necessarily the way to go. But if we get this working right, you're going to have everything you need to understand and use more complex binary formats in a very simple way. All right, should we just leave it at that for today? Or do you feel like we should use the last, we have 20 minutes? We could do some fun stuff. Any requests?
Got one request. When you're looking down and then you want to rotate, without rotating like this, how would you rotate around your up vector?
Yeah, not rotate around your actual V vector on the camera, but rotate. I don't think I've implemented this myself in here, but I did write it on the. I did write it on the whiteboard the other day, and someone actually wrote it up. Okay, so what I would do, let's just look at it in code here. Model matrix is, no, not model matrix, camera is where we're at. Okay, so we have here yaw. Let's just look at the difference between yaw and what it is that you want to do. So yaw here, what we want to call this? I don't know, yaw floor, or rotate, maybe just rotate Y. That's nice. Okay, so we want to rotate around the base coordinates y-axis, but not actually with our point around it, but around it as if it were exactly where we are. So there are two ways we could do this. We could set up a Y rotation matrix and then multiply that, not to the right side, but to the left side of our camera coordinate frame, but without the I coordinate. That's one way. If you just understand how the transformations work, you can just add that rotation transformation to the rotation part of our camera matrix and you've got it. But the idea behind that is that here we're only using U and N to set U and N, and V is basically being ignored. We don't need data from V, and we don't need to change V because we're rotating around V. When we now want to, you imagine that V has already tilted forward, but you want to rotate around the vector straight up, which would be 0, 1, 0. You want to rotate, then you actually need to change all three vectors. You need to change V as well, because V will have tilted forward, and now you want that to go this direction. U will have gone here, and you want it to rotate, and Z or N as well will be tilted this way, and you want it to rotate. So you need to rotate all of them, and you need to rotate them around the Y vector, or around the Y-axis. So you can rotate each of them independently, without using any data from the others. So if we go here, we don't need this T here. So we have U set and N set here. So what we want to do is for each of them we'd like to do U set, and we're rotating them around Y. So we're changing the X and Z coordinates of all the vectors. Whereas before we were changing the U and N vectors, but not V. Now we're changing the X and Z coordinates of each vector, but not the Y coordinates. Otherwise we're doing it in exactly the same thing as we're doing up here. That is, we're going to take X, U set, and its X coordinates will be UX times C minus, no, not N, U Z times S. I can actually do it the other way around. Say it's kind of minus S times this. So C cosine. So can you see what we're doing here? We're simply rotating this vector. We're doing a y rotation on this single vector. And this here will just be uy. We don't want to change that because the vector is rotating like this. Its y coordinate is the same. Then here we're going to end up with the sine times u dot x plus cosine times u dot z. Okay, so everything in this line is from the vector u. We're rotating u independently from the others around the vector 0, 1, 0. So it's the vector 0, 1, 0, so this will be unchanged. And these will be basically in the same way as u and n were affecting each other earlier. Now the z and x coordinates are affecting each other in this rotation. Then we just have to do this for all of the vectors. So v will be changed independently of the others. And n will be changed independently from the others. And then we don't even need to save a vector because we're basically using all of its data here and then sending it in, and then we don't need to use that vector again. Okay, so we're not doing this anymore. We don't need this. The same idea with the angles. We have radians here, we have the cosine sine. Then we change each vector independently. And now, to make sure that I'm not lying to you, let's see if we can use this. So let's first look at how it works now. Okay, so I'm basically at level with what, the fourth floor of these pyramids. And then do this, and then I go up. And obviously, when I rotate like this, I'm going all over the place. Ah, yeah, I haven't changed the... Oh, never mind. I haven't changed the slide function to do it as either. I should actually do that. Okay, so I'm going all over the place. Let's see now what happens if we go into... I should actually change the slide function. Or not change it, but make a separate function here. So we have the rotate y function, and let's just call this the walk forward function. And it just takes some delta here, doesn't matter. So now we're only interested in the n vector, right? Okay. The negative n vector, actually. Yeah, so this is just this delta. Okay, we'll do minus, and we're not interested in changing the y coordinates, right? So this is one way. Let's look at it again. We might want to normalize this because this means that if you're looking really high, you're going to go really slowly. Okay, so now I'm going to go into my game. And I am going to go in here and see where we're using W and S. So let's go and say cam dot walk forward by 3 times delta time. That's W, and S be walk forward by minus 3 times delta time. Don't need a walk backward function specifically. And the other one is yaw, where instead we want to say cam dot rotate y by that same angle. Like so. Here. And like so. Now just let's see what happens. Okay. To begin with, I'm rotating in the wrong directions. Doesn't matter though. Just clockwise versus counterclockwise. Okay, but it seems to be working now. Let's look up and walk forward. Okay, I'm still, doesn't matter how much I look up, I'm still always level with, but you can see how much slower I'm going when I'm looking up. If I look up now, okay, that skewing isn't actually happening. It's just I have such a wide lens. So if you just go somewhere like into this, look up. Okay, I'm near plane clipping there, like so. This is pretty cool though. Okay, so yeah, you can look up here, whoa, you can look down, and we can look up and down and rotate at the same time, and we're still keeping level with the 4th floor of this at all times. So does that answer our question? No problem. So now we just have like 7 minutes left that we need to kill. No, this is fine. If there are any questions or anything you want to see, feel free. But yeah, next week we'll look at the meshes better. We'll look at textures, and especially in the lab class, we'll get all this together and work with it a little bit, because you're going to need some kind of model or something in your last assignment. You don't have to use this model, this file structure that I'm using if you don't want to. But I'm going to give you a lot of code to read that. But if you want something more versatile or something more powerful, you can just find online like third-party file loaders and stuff, and just find out how you can load the files and then read the lists into your structure. And you know, it doesn't have to be more difficult for you to do that than to take mine. So it's your choice. But yeah, have a nice weekend.